This is Tom Gardner, representing the Computer History Museum. We're here today, October 9th, 2017, at the offices of Awida Venture Capital in Superior, Colorado, to interview Richard D. Richard will go through his background in a few moments, but let me simply say that Richard is a technologist with experiences at both Storage Technology Corporation and Quantum. At one point he was the StorageTek Fellow, and his area of specialty that we'll discuss today is recording head technology in tape drives. So Richard, tell us a little bit about yourself.
Okay, as you can tell from my accent, I'm British by origin. I was born in England a long time ago, and there I got degrees in physics. I went into the field of physics, and got a PhD in physics in the end, and moved to North America to do research at the universities. I was at the University of British Columbia for 3 years, and then at UCLA in the Department of Physics there. And after that I worked in low temperature superconducting magnetometry, and from there I was recruited into StorageTek.
Let me back up, and where were you born? In what city?
It was in Barnet in Hertfordshire, just north of London.
Your mother's maiden name?
Good question. That's actually a bit secret, because that's the question they always ask you on all the websites.
On all the websites, that's
right.
correct.
So I can't reveal that, otherwise some people can get into my accounts.
That is true.
Right.
And your parents were from the same cities?
Yeah, they were born in London.
And what university?
I went to the University of Lancaster. In the north of England.
That's where you got your PhD?
Yes, that's right.
And how did you get interested in physics?
Well, I guess it was at high school. I was pretty good at math and science, but not very good at languages and history and stuff. So the fact that I did well at it made it more enjoyable. So I think I went into the sciences quite early on at high school, and then decided to go to university to study physics. I almost went into a career in electrical engineering. I was recruited by the electrical supply industry in England to train to be an engineer. But I only lasted there 3 weeks, and I went to university to do physics instead. So,
why only 3 weeks?
Well, in England the system at the time was you got these exams, entrance exams to university, and I didn't know the results. And I said, well, I really wanted to go to University of Physics, and the people that worked at the electrical supply industry said, well, you can start with us, and if you get into university, fine, you can go, but if you don't, you can stay. So I worked there for 3 weeks until I got the results and a place at university, and then I left. So,
are you married?
Yes.
Children?
Yep, three daughters.
Your wife's maiden name?
Ross, in that case.
Ross?
Yeah.
Okay.
And,
you then went to British Columbia and did some research in the university there?
Yes.
And
I was a postdoctoral fellow there, worked in low temperature solid state physics to do with superconductivity in inorganic and organic compounds rather than metals. So that was the hot subject at that time. So. And the one material I was working with was called polysulfur nitride, made out of sulfur and nitrogen, and strangely enough it was a superconductor at 0.3 Kelvin, so we worked on the properties of that material.
And then to UCLA?
Yes, I was an adjunct assistant professor at UCLA in the physics department, but I was only there 18 months because I was looking for a permanent job. That was only a temporary position. So I was looking for a permanent job almost the day I arrived. But I taught physics there and did research and looked after the graduate students and so forth in the lab. And then finally got a job in industry, essentially in a company in San Diego that made SQUID-based magnetometers, SQUIDs standing for superconducting quantum interference device. So,
And when was this about?
1980?
More or less.
Yeah, 1980. 1979, I was still at UCLA, I think, yeah. Right.
And what was your specific activities on SQUIDs?
SQUIDs, well, I basically just used them. Okay, I didn't actually make them, although I did make some mechanical point contact squids at UBC to use. You can make them we made them in the machine shop. They weren't thin film devices at the time; they were mechanical ones, but they worked great.
So, what did you use SQUIDs for?
Detecting very small magnetic fields, really small. You know, small down to 10 to the minus 6 Gauss or below, looking at small changes. In these superconductors that we were looking at, we were looking for the magnetic expulsion that you get due to the Meissner effect, and in this material it was really small.
The what effect?
The Meissner effect. When a metal goes superconductor in form from a normal to a superconductor, it expels all the magnetic flux from its interior. Okay.
Okay.
That's a phenomenon of superconductivity.
And
so you can prove that that material is a superconductor if that happens.
Gotcha.
Because it only happens in superconductors.
So that's the beginning of your serious work in magnetism.
A little bit, yeah.
Yeah. Somehow you wandered or went from that company to StorageTek?
Yes. And that was because a lot of times they always say it's not what you know, it's who you know, but and it's a bit of both sometimes. In this case, that was the case. There was a gentleman who worked at the company in San Diego who was from Boulder, Colorado. And him and his wife decided to return to Colorado. And so a few months later, about 6 months later, I got a phone call from him because I worked with him closely at a company in San Diego. And he invited me to go and work at StorageTek. And it took him 2 attempts to get me to come here to StorageTek, primarily because of the job that was being offered.
The first job was not so interesting.
No, it was a manufacturing position that really wasn't my forte. So, but then 6 months later, he phoned back, and I came out to visit, and it was a job to develop thin films for magnetoresistive devices in tape heads. Because at the time, StorageTek had a fledgling group that was doing some advanced R&D work in that area. And they needed someone, I think, that understood magnetism and thin films, which I'd worked a bit in thin films at UCLA and also at the company in San Diego. They made thin film SQUIDs there and other thin film magnetometer types. So,
did you name the company in?
It was called SHE Corporation. SHE.
SHE.
Yeah, it stood for superconductivity, helium, and electronics. Okay. So it was called SHE Corporation, and doesn't exist anymore. It morphed into something else, as a lot of companies do.
Mm-hmm. So the second time was a charm at StorageTek.
Well, yeah, that time the work seemed more interesting. It was a research and development job, and they invited me out to Colorado, and of course I fell in love with Colorado, which is not difficult. And me and my wife decided it was a good move to make. So we left San Diego. We like San Diego too, but I think we like Colorado better.
So now you're in the world of tape heads.
Right, which was unusual. This was the first time I'd had a job where everything was at room temperature. Because I've been working in low temperature physics, which practically everything had to be done below 4 Kelvin. And quite often below 0.1 Kelvin to see what we were looking at. So this was quite different. It made life a lot easier, let's put it that way, okay?
In some ways, I presume.
Yes.
In some ways, not so easy.
Some ways not so, but to do the experiments and the design or whatever it is to room temperature, rather than hanging it on the end of a stick and dipping it in liquid helium, made a big difference. So,
So what did you find when you arrived in this research group at StorageTek?
well, what I first found was they put me in a cubicle, and I got some strange looks, because the Friday before there was a different person sitting there and they got laid off, and this was kind of disconcerting, at least for the first week or so. But no, I found that we were in a building 6 over here on campus, on StorageTek campus, and it was because downstairs there was a clean room where they were developing a thin film disk head for their upcoming disk drives, using plated permalloy and copper coils and so forth. And they felt that this tape fledgling R&D group could use a lot of the vacuum system, and the clean room for that matter. They didn't particularly want to build another clean room at the time, so we borrowed the clean room. And we were supposed to, and I was there to develop a magnetoresistive thin film. That they'd already started, but were not making a lot of headway, apparently. So there, the first thing we tried was they were trying to evaporate a permalloy to make the thin films.
Just one interruption. This was now before there was any magnetoresistive tape heads shipping in any disk drives.
Oh yes.
This was before the IBM 3480.
Oh yeah.
Okay.
Mm-hmm. Yeah, that was a tape drive, by the way. But yeah, but yes, tape drives, as you know, came out with magnetoresistive heads many years before disk drives did.
This was before any tape drive was shipping.
Yep.
With a magnetoresistive head.
Yes.
Yeah. So somehow your group was anticipating the future direction.
Right. Not quite sure how, or whether they got some intel from somebody, I don't know, but there you go. That's the way the industry works, right? You typically go to conferences and so forth, and you see what's going on, and you can put 2 and 2 together quite often.
Was it 18 track at that time? Or just a lot of tracks?
No, I think it was 18.
Okay.
Yeah, I think it was 18 from the get-go. So obviously there was some information that was coming out that the next... Well, everything was 9 track up to that time.
Right.
So 18 was a doubling, and so that made kind of sense. Because pretty much capacities and so forth in tape drives for a long time have been doubling. And so yeah, it was. I think it was 18 from the get-go. And we managed to make 1 or 2 tracks work now and again at that time, but that's what R&D is all about. Yeah.
So what were some of the interesting experiences during this development
okay.
stage?
Well, one of the first things that I discovered. You asked me what I discovered. Okay. One of the first things was we're evaporating these thin films, and you had to evaporate them onto a substrate that it was an elevated temperature, 200 centigrade or so forth. And the first thing was, from a technical standpoint, was I said, well, how do you know what the temperature of the substrate is? And they had this thermocouple stuck on the back of this substrate with a big heat lamp on it. And I said, I can tell you this much, that your thermometer is probably at 200 centigrade, but I've no idea what the temperature of the substrate is. So the first thing we had to do was to figure out what the temperature profile of the substrate plates were. And it took some time to feed in thermocouples on the front surface and characterize it. We did temperature time curves to figure out that the temperature on the back on this thermometer had to be considerably different if you wanted the surface to be at 200 centigrade. So we fixed that. And the next thing that happened was they were using test coupons on silicon substrates to measure the magnetic properties of the films that were resulting from this. And they used this looper machine, which we used to call a Bacon tester. In the industry again, a man named Stanley H. Bacon, I don't know whether you've heard of him.
I haven't.
He made magnetic loopers to do hysteresis loops. And I think everybody bought one that was doing this. He made quite a lot of them. And you put this substrate into these coils that excite the film, and then you detect the resulting magnetization change, and it plots it out on an oscilloscope as a hysteresis loop. And there were certain properties you needed, which was a high magnetic anisotropy had to be in this MR film. In other words, the magnetization had to align on a very strong easy axis, they called it, where the magnetization would prefer to lie, even with no magnetic field applied. And so you had to rotate the sample to see what the anisotropy was. And I noticed that the tech that was running this put this film in, and you got this horrible looking magnetic loop that wasn't what you wanted. And he said, oh, well, if you turn this knob, it looks great. So he turned this knob on this machine, and the film looked perfect. A lovely straight line hysteresis loop in one direction and a perfectly square loop in the other. Great anisotropy, right? I said, what does that knob do? He said, I don't know. Okay. And I said, well, we've got to find out what that knob does. Okay, and all it was doing was applying a DC magnetic field in one direction across the film. So it was aligning the magnetization before you did the excitation. And I said, we need to get that film to look like that perfect loop that you wanted without that knob being turned. Okay, the film has to do it, not an external field. And so when we got the temperature fixed, we got the applied field in the deposition fixed. It didn't take long, only about 2 or 3 weeks, about a month after I arrived. We got the films to run with the correct anisotropy without faking it with this DC bias field that was in the Bacon tester, we called it. And that film was the first one we put into a head to test. And fortunately, that first prototype head actually worked. Really? Out the gate. Once you got the film correct, it was fine.
Were you at single element or 18 elements at this?
We had 18 elements, but we didn't wire them all up because we didn't have any good wiring schemes then. It was basically a jeweler we hired to hook up little wires with a little tiny soldering iron. His name was Joe Shaps. He had a jeweler's down in Boulder, and he worked at StorageTek in our lab to do the very fine work. He used to fix he was great at repairing antique watches. That was his skill. So we had him in the lab to do all this little fine work on these devices.
Yeah. As I understand it, in tape head technology, one of the challenging problems is getting all the wires out of an 18 or a 36 track head.
Yes, the interconnect. There's a lot of wires. There's two for each channel, plus a few hangers on, right? That's a lot of wires.
In a small space.
Yes.
Yes. Creates.
Yeah, we used to fan them out a bit, to help them get a bit bigger, but it's still pretty small. And then you had to wire them all up, so there's like 40 or 50 connections, and they all had to be good, every time, right? And that was a challenge. But initially, the first head was essentially discrete wires that were hand soldered by Joe Shaps. He was good at it too. Yeah. So
tough to scale.
Yes. No, that wasn't the point. See, we were the R&D group. We were proving the science and technology of the devices themselves. The scale up to batch fab the whole structure was the next step. The masks were made to do that, but we only tested a few of the devices initially.
So this is now 83, 84?
Yeah, 83. Yeah, and 84. Right. And during '83 we came up, we started to work on the interconnect with a flexible circuit, a flexible printed circuit with copper leads on a capped-on base with the same pitch as all the pads on the thin film device. And the initial connection system we used was ultrasonic bonding, gold to gold. So you plate gold on the flexible circuit pins sticking out, and gold on the thin film circuits. You lay them on and come down with a high pressure ultrasonic energy source to try and bond them together. And that worked after a fashion, but it wasn't very reliable. Films tend to peel up, and that's not good. Okay, and eventually the technology we used was stitch bonding, where it's a thin aluminum silicon wire with which comes down and bonds onto the flexible circuit pad, and then loops over and bonds onto the thin film. So there was it wasn't as rigid and brittle as the other contact. It had some flexibility, and this thing used to be programmed XY, so it would stitch along and stitch all the wires automatically.
Now, this was still a storage technology unique design. You were designing it to your own parameters that
Yes.
were intended for an OEM product or intended just as a research product anticipating an IBM product?
Yes, anticipating IBM's 18-track product coming out soon, which came out, I think, in 1985, if I'm not mistaken, 3480. Came out with a magnetoresistive 18-channel head.
I think it was announced in '84 and shipped in '85. We can check that data.
Yeah, right. So we had in place in '84 already the MR elements, which were differentially biased and sense elements. They weren't singles. They were center tapped with the differential bias. And we had that already in 18 channels. And the right head was several turns of gold with a ferrite base for its magnetism, and to form the right gap. It was between two ferrite blocks. A thin film right coil.
Was this a right read right or just a read right head at this point?
Yes, one module had 18 readers on it, and one module had 18 writes. So it only ran tape in one direction, in one pass to fill the tape. So.
And this was working in the lab?
Yep.
And then the IBM product is announced?
Yes.
And then you get an IBM product?
Yes, that's right. StorageTek was one of the first customers to buy one. And of course it was interested in how it could make a tape drive, because it was already working on it, such that it was compatible and in interchange using the tapes. So they could read and write the same tapes as IBM in that case. So, our head was a slightly different design than theirs after looking at the IBM head. Of course it would be, because different engineers and scientists developed it. One thing I learned years ago, if you give two groups of engineers the same problem, they'll come up with different solutions. And that was the case here. It was 18 channels. It was a differential MR head. That was the same, a thin film right coil, but they were different designs magnetically. The right coil had more turns. The read head was biased differently. The MR head was biased. It has to have a DC field applied to it to linearize it, and that was done differently in the storage in our design compared to what IBM used. And we didn't change it. The only thing we changed from what we ended up with to make it compatible was we dropped the right head to 2 turns from 4. So that was how we ended up with a compatible drive. And also the other thing we did was we didn't guess the track pitch correctly, so we had to shift that. But that was
the
easy.
Track pitch or the track placement or both?
Probably a bit of both, yeah, and the width.
Yeah, you have a half-inch tape,
Right.
and you have 18 tracks, but exactly where the tracks are,
Right.
guard bands,
Exactly.
and the width of the element.
Yeah, we'd come up with our own set of numbers for that. And IBM's drive was slightly different, so we had to be compatible, so we shifted those dimensions.
Yeah.
Yeah.
My understanding from our early conversations, it was pretty close.
Oh yeah, it was very close. In fact, so close that I think it was the Christmas break of '85. StorageTek was still trying to decide whether to where it could buy this head. It didn't want to manufacture it. It'd been buying tape heads from other manufacturers for its whole lifespan, and of course couldn't buy one from IBM. So one Christmas I came in with another engineer, and during the break when no one was there, and he was pretty skillful in removing, aligning tape heads and tape paths and things. So we took the IBM head out of the IBM drive, put our prototype head, one of the ones that actually worked, okay, had 18 channels working, put that in and aligned it according to the same measurements he'd made from the IBM head. And we plugged it in because it turns out the connectors were the same. That was another bit of serendipity, okay? The connectors were the same, so we just plugged it straight in.
Really?
And ran the diagnostics and the error statistics, and it matched the IBM numbers with the IBM head in there. Even though it wasn't an exact clone, the MR head was different, had different resistance and different biasing scheme and so forth. And the right head was 2 turns, but it had a different back structure in terms of the ferrite. It was more efficient. The IBM head used to run on 190 milliamps, if I remember rightly, and ours ran on 150 or 160 milliamps. So our head ran with the wrong current, but it still wrote just fine. And took the data, wrote the report, and put the report on the director's desk, so when he came in January the 3rd, he would read that. And that's what made the decision for StorageTek to set up a manufacturing line to make thinner film MR tape heads.
Mm-hmm.
So.
Was it more than system or subsystem diagnostics? Did you also do analog type measurements, resolution, things like that?
No, at the time, the only thing we had time to do was to really run data.
Okay.
And look at the error counts, you know.
Okay.
So, but it turns out that it ended up that recording channel with that tape, the chrome dioxide tape, and it had a lot of margin. So you could run, like we ran the right current way over the right current past the peak, but it was still wrote fine. And I'm sure that the read signals might have been a little distorted, but it was a peak detect channel, and as long as it was in the timing window, didn't matter if it was a funny looking waveform, as long as it was above the threshold within the timing window, then it would deliver the correct data.
At that time, was the head tape interface design the same as IBM, or what was the?
It actually it wasn't. It was I think originally the design we had straight cross cuts in the ferrite surface to scoop the air off, and IBM came out with parallel slots so that it would lighten the contact pressure. Because it turns out chrome dioxide tape was the next best thing to sandpaper, in my opinion, okay, for scraping over heads and wearing them out. So I'm sure IBM made it such that it wasn't pushing down quite so hard on the surface to extend the head life. And it didn't take much. I mean, even with IBM's contour, the wear pattern was a wavy line right across the head, down where the elements were, where the slot was in front of it, it would wear, and in between where the air would run, it didn't wear. So it was a compromise contour over performance versus life, head life.
So in spite of a more efficient right element and a slightly different had tape interference, the head from the lab read and wrote in an IBM drive to the standards of the IBM diagnostics.
Yes.
It's pretty impressive.
Yeah.
So in looking back in your mind, comparing the two heads, walk me through a comparison. Which features you think were better, perhaps in the IBM design and better in your design?
Well, I'm very biased here.
Of course.
Clearly. I think the better in our MR head design, the biasing technique we used was called offset in the gap. So there's two magnetic pieces that formed a gap, and the MR element wasn't in the middle, it was off to one side. So when the sense current runs through the MR element, there's a magnetic field that couples to it and provides you the bias field the MR head needs to linearize it. In the IBM head, they did a little bit of that, but they ran 2,000 angstroms of titanium as a shunt beside it to draw some of the current, so that the current delivered the field you wanted. However, if you shunt it, the word shunting, you shunt the signal too. So the output was lower, and there was this huge 2,000 angstroms of titanium next to the MR element that actually wasn't necessary. So it wasn't in our design. We didn't think to put it in because...
Never put it in.
No, you could get the bias field you want just by offsetting it more. Now, the bad thing about the offset, if you want a negative thing, I have to think of something negative, okay, is that when the tape runs in this direction, the waveform looks different than when it's running in that direction. It goes lopsided. It's a phase shift, and the channel has to deal with that. So that could be perceived to be a problem. As in the IBM design, that was less so because it was nearer the center of the gap. So
we'll probably
that's a design detail. But
sure. We'll probably return to it. But at this point, I understand you are the lexicographer for the tape axioms or recording axioms. You have 3 of them?
Oh, yes. Yeah, I came up with what I call the 3 axioms of storage devices, not just tapes.
Understood.
It was at I gave an invited talk at the NSIC annual meeting in Monterey many years ago, and it became clear to me over the time that there were 3 things that governed everything in storage devices, and axiom number 1 was that the media is the problem. Okay, it causes all your problems, and it determines what you can and cannot record: densities, speeds, feeds, everything. Axiom number 2 is the head is the messenger. It's telling you what the media is doing wrong or right. And axiom number 3 is the channel has to understand the messages, and they have to stop whining about that, because they're always shooting the messenger. When the channel guy looks at his signals, he always blames the head. The first thing they did, they changed the head out. But 9 times out of 10, it's the media is the problem. So
I interrupted you there because you talked about the channel having to deal with a phase shift, and that brought out...
In that case, the messenger could speak with a forked tongue because of that offset. Because sometimes the tape drive would read backwards.
Right.
That 3480 and StorageTek's 4480 would be asked to read backwards.
Right.
Okay.
Which brings me back to this first head now being put in the IBM drive. It was a read backwards head, meaning it had a read element with write elements on either side.
No.
No.
No? It would read the tape that was already written backwards. So you write the tape this direction and read it, read while write, and then at some other time it stops and it wants to read something back there, so it just reads backwards. It reads the data in reverse order. It's not writing, it's just...
No, it's reading.
It's just reading, yeah. And, but even though our head had this asymmetry, the channel had enough margin that it could absorb that.
That was the point. I was getting to the IBM. Well, yeah, the IBM channel could deal with your head, which had the different asymmetry.
Yes.
Now, the STC channel was then designed to deal with the asymmetry.
Yes, I think it had two different settings for forward read or reverse read.
Okay.
Yeah.
So you mentioned 4 turns versus 2 turns, but in the production head, you went to 2 turns.
2 turns.
That was an engineering decision, a management decision?
No, I think at the time that was a management decision. They wanted it to be compatible with IBMs, and they thought the head might be more compatible if it was 2 turns. It turns out it made no difference at all, especially as our 2-turn head, as I mentioned, was much more efficient than the IBM design because of the way their coils were laid out. So the write current in our head was 30% lower than theirs anyway. So even though it ran in a tape drive, the optimum write current would be different in the 4480.
And then with 4 turns, the current would have been reduced by another factor of
2, yeah,
2.
which we thought was a good idea. The head dissipation, was different, and the amount of power required out of the tape drive would have been lower. And I think like I said, I think the rise time was sufficient to give the recording characteristics correct.
You mentioned transverse versus longitudinal slots.
Right. In the head.
Either one better, different, does it matter?
At the time, with nickel zinc ferrite as the base for the head, the magnetic pieces, I think the slots across the head wouldn't have survived very long. The corners would have worn off, and the tape would have started to fly. So essentially, the 4480 head came out with exactly the same contour as on the IBM head.
And probably the right decision.
Yes, there was one change we wanted to make, but again, that was turned down because it was too late in the manufacturing cycle. On the edge of the tapes, there was 2 slots in the same direction of the tape, where the tape used to droop into these slots. And that was to cover the problem of debris accumulation on the tape edges. And there was 2 slots each side, and a piece of ferrite in the middle that used to wear off. So track 1 and track 18 used to wear down, and then the head would fail. And we came up with another idea where they only had 1 slot, put more ferrite out there, take the inner slot out, and then track 1 and 18 didn't wear out. But that was never introduced.
So how long did it take then from the time you got the 3480 head until you then had a head you felt was suitable for a storage technology?
Oh, yes.
Tape drive.
I can't remember. I can't remember when the 4480 actually came out, to tell you the truth. Whether it was 86 or 87. I can't. You know what? Sorry.
We'll put the date.
Can't remember.
In the transcript.
Yeah, but the head was the technology gating item. Clearly, without that, there was no tape drive for StorageTek if we didn't actually make it.
Now the production design was actually done in a different group than yours, and you guys went on to the next generation.
No, we actually took the head design and processing. The groups were blended for a while. The R&D group and the advanced manufacturing group were blended for a while, and then when everything was fine, we back out and went back to R&D again to do the next head.
For what it's worth, Storage Technology announced it in March of '84 with general availability in the first quarter of 1985.
Oh, wow. That's quicker than I remembered.
Now, sometime announcements of availability don't occur, but that was the official announcement and the stated availability date, first
Okay.
quarter 85.
And so this head was the first head that StorageTek had ever manufactured from raw material
Yeah, no,
on site here at on the Louisville campus.
prior to that, Storage Technology had purchased heads.
Yes.
Why didn't they purchase this one?
Well, they used to buy heads from Applied Magnetics and Nortronics. Used to make the big 9-track core winding type heads. And it turns out that those two companies couldn't come up with a thin film compatible head in the time frame that was needed. A couple of them came and gave us presentations about designs, and they were completely, I wouldn't say they were alien to us, but they were completely different. Not a ferrite head with 2 turns of gold in between, a very simple design. They were the complicated, more plated thin film disc type heads, which had multiple layers and multiple thick permalloy magnetic pole pieces, which unfortunately didn't respond fast enough to the 45 nanosecond right equalization pulses you need to get through to the tape in that product. One of the principles that drove us in the design originally was because we had to have so many channels all working in one process, the processing had to be kept simple, because every time, it was like all thin film or integrated circuit work, the more you touch the part, there's a probability of getting it wrong or having an error. You know, you can have 99.99% product correct at every step, but you multiply that together and you get a lot of yield drop. You have to have all 18 working all the time at every step. So the processing that we had on the right head only involved one photolithographic mask, okay, to do the whole right head. Okay, the companies that were proposing what they were going to do had about 10 photolithographic steps.
3.
Okay.
Okay.
And we had one.
Sure.
That one photolithographic step defined the coil, plated it, and you evaporate the coil through it, and lift off your photoresist, and the right head thin film was finished. And on the magnetoresistive head, there was only 2 mask steps. One for the MR device, and one for the overlay, the copper gold overlay on the back leads. So in other words, 3 masks to make an 18-channel read-write head.
Or 3 masks per channel.
No, you do all 18 at the same time. Okay. So in other words, the mask had 18 images, which you put down and whack, and exposed it, and done in one go. And the right read head only had 2 masks, and the right head had 1. And you had an 18-channel read-write head finished in the clean room. So the yield was pretty good.
Yeah.
Okay. As these other designs, the yield was terrible. The AMC sent us some prototypes back in '84-ish time frame, and only 1 channel would work. And we said, well, that's not quite good enough. We need 18. You know? So the processing went down to building 8, where the thin film disc heads were being made to utilize the clean room down there. So, and that was in 80, I guess it was late 80, 85-ish to do that. So, of course, that was after StorageTek had gone Chapter 11, so, which made life interesting. But.
So at this point, we've finished talking about the 3480 class of heads,
Right.
Which Storage Technology produced a different head, but was fully compatible in several ways, in your opinion.
Yes.
A better design. And so now, at this point, the group moves on to the next generation of heads?
Yeah, that product was shipping, so the R&D group thought about what was going to come next, and as tape capacities have been doubling every time, and the next doubling, it was fairly straightforward to double the number of tracks. Because if you do that, you can use the same tape, and you can use the same channel, you can use the same cards and everything, and just produce another tape drive at twice the capacity. Okay.
Well, to use your term, the message from the head may be a little
different.
A little different because the areal density has now gone up by at least a factor or two.
The areal density, yes.
Areal density, yes.
However, as you know, the track widths at that time were very large from what we're used to now, and even shortly after that. But clearly the requirement from the channel group was that the output from the read head had to be the same, even though the reader was going to go down at least a factor of 2, and probably a bit more, to allow for mistracking, because it was right wide read narrow in this sense. So if you're going to halve the writer width, then the reader had to go down a factor, and probably a bit more. Went down a factor of 3 almost, I think. But the output had to be the same. Okay? So
that sounds like an impossible task.
Well, unless you know what you're doing. Okay, so when you do an MR head, you know that the output is proportional to the change in resistance. And the MR ratio for a permalloy element is about 2 to 3%. So if you want the same output, the ratio of the change in resistance over the resistance is still going to be 2 to 3%. So the way to get the change in the resistance to be the same, you just have to raise the resistance of the element, or make the resistance of the element the same as it used to be. So for the wide reader, if it was, say, 30 ohms, you have to make the narrow reader 30 ohms. And to do that, you just reduce the width and the thickness of the element. And that's all we did.
Pure scaling.
That's all we did, just scaled it. And got exactly the same output that the 4480 had with a third of the track width. And the read-write group thought it was a miracle, as you just said. But it really wasn't. It was just scaling. And you can keep scaling MR heads for a bit more than that, probably, as disk drives demonstrated in the 90s. But it was, again, it was a full differential bias, differential read, a differential sense, and it was exactly the same as a 4480 head, only scaled down. So, in other words, really didn't have to do much, which is why we got it out fairly quickly. And the write head was the same. Again, 2 turns or so on a ferrite base. The only difference between the 36 channel head and the 4480 head was the 4480 had one module which was all writes and one that was all reads. And for the 36 track to go, so you want to read and write in both directions, you interleaved them. So there was a writer and a reader, a writer and a reader. So on each module there was 18 writes and 18 reads side by side, interleaved. So you first did the write process, and then you came back and did the read process. So what we did is we essentially did the same process, thin film process that was on the 4480, interleaved on the same substrate. And then once you'd done that, you just cut 2 of these modules and turn one over to face the other. And there's a reader downstream from this writer and a reader downstream from that writer. So you can do both directions. And we got that head out, the prototype out fairly quickly, and tested it, and it worked just the same as a 4480 head, pretty much. Put the report on the director's desk that we'd done this 36 channel head to double the capacity of the tape. And just by miracle or fortuitous, the very next day IBM announced their 36 channel drive, and it was to be this doubling track density, 2-directional tape motion that was compatible with this 36 track head that we'd developed. Again, the only difference was the reader width wasn't the same as the IBM's head when it eventually came out. We saw it, and the track pitch wasn't quite exactly half or something. They'd shifted it over a little bit, and didn't know why, but we had to be compatible, so we moved ours.
So
So that head really, even though it seemed more difficult to do and everything, the people in the clean room, in the R&D clean room, did a great job in merging those two things. There was one photolithography expert, Maribel Blakesley, a lady who was an expert in dual layer photoresist processing, which we used a lot for the right head process. She was the one that whizzed this, you know, the original design of the right head, and this interleave design. And it was done in, by that time, StorageTek had invested in an R&D clean room for us, so we had our own space. So we were able to work independently of the manufacturing line, or vice versa. They were able to work independently of us, because as you know, if you try and do R&D on the manufacturing line, all the manufacturing engineers don't like it because you're disrupting their processes. But, so that period of time when we had our own clean room enabled a really pretty fast 36-track development. And beyond that, we even developed a 72 and a 144 in parallel with that. And we offered it to StorageTek, saying, well, you can do a 72 and a 144 track, okay, with the same design on chrome tape. But they were in the mode at the time of being IBM compatible. So if IBM wasn't going to do a 72-track tape on chrome, then StorageTek wasn't. Okay.
And would this be the same concept of just smaller...
Scaling more.
Scaling more, mm-hmm. So you'd have...
there was enough...
In the same 1/2 inch or approximately 1/2 inch
yes.
Wafer, you would now put down
right. In fact,
72 elements.
Well, the 72 element, or 72 concept, because we still, the industry, tapes anyway, weren't using track following servo at the time, the concept there, which we upped from the head group to suggest to the company, is that you take two 36-channel heads and offset them to get your 72. Just scale the widths of all the channels. Just stick two heads in. That was turned down because that would cost twice as much, apparently.
At least for the head part of the drive.
Yes, right. So, and the same sort of idea for 144s. Or you have what they call a bang-bang head, where it had two positions. No servo, you just move it on an actuator up or down against stops. And that was the concept then. But none of those transpired. Primarily because IBM never went to a 72 or a 144 follow-on.
And as near as you could tell, management was not willing or interested in pursuing OEM opportunities.
I guess not at the time, no. And later they did, by the way. But as a result, there was a lull in products, StorageTek tape products, between the 36 and whatever came out next, which we'll talk about if you like. Because there was no, I don't know, there seemed to be a long gap, several years, of not knowing what to do next. I mean, we came up with the 72 and the 144, you can do this next, you can do this next, you know, but that never transpired. And then the concept came up, I don't know who suggested it, who suggested it from the tape group. It wasn't me, but was to be do a tape drive that wasn't compatible with IBM, and that was the what was called the Eagle drive then, and it came out as the 9840. And the 9840 was a totally different tape drive thing compared to what gone before in terms of the IBM compatibility direction. It was a two-reel tape with a center load head, a cartridge, as opposed to a tape reel that pulled out and spooled up on another reel. Both reels were in the cartridge. It was a cartridge drive, not a tape, separate tape spool tape drive. Mm-hmm. And this was to speed up the access time to data. In other words, you didn't have as far down the tape to run.
half the distance?
Or it'll be about a quarter. I mean, oh yes, at least half, because you're in the middle.
Right.
You start in the middle. And that's where you put your directories or your startup files, is in the middle. And then you either go that way or that way to find the data. It was called fast access tape, which at the time, it was faster.
Mm-hmm.
And that concept came up. I'm not quite sure who it was. And they came to the head group, what needed to make a head for that. Now it had to read and write in both directions, and do a lot more tracks to get the capacity up, which is where track following servo started at StorageTek on tapes.
So you did the head.
Yes.
It was how many track?
It was 18 channels.
Excuse me?
18.
18.
It wrote down 18 tracks at a time,
Mm-hmm.
but then it stepped over n times to, I think the first came out at 144 tracks on tape, and its follow-on was 288, and then its follow-on was 576. This is in the sequence of tape drives, so on the same cartridge. And the tape in there was different. It wasn't chrome dioxide anymore, it was metal particle tape. And that was manufactured, and the cartridges and the tapes made by 3M, or Imation, because Imation started about then, didn't it? Came out of 3M.
Yeah. You didn't date the 9480.
It was mid-90s.
Mid-90s?
Yes, 9840.
Mm-hmm.
And it was a center load cartridge for high capacity. I think it was, the first one came out at 20 gigabytes, which doesn't sound like a lot now, but anyway, it was a lot then, okay? 20 gigabytes, and it was 144 tracks on tape. And the head design for that was interesting. Because you had to read and write in both directions, we went to an 18-channel write head, a 3-bump head, 3 modules. We had a write head, and a read head in the middle, and a write head. And they're all in the same line. So you could write this way and write that way and read after write, in both directions. And the write head design was a thin film.
That's a process change for you guys.
Yeah, we went for out, because metal particle tape, the coercivity was much higher. You could not use ferrites. You had to use a higher magnetic moment pole piece.
And you're still making these heads here in Colorado. You're not outsourcing them from a third party.
Correct. So we developed, in this period where there's this gap, in that period we developed various pole processes for tapes. We used plated permalloy, not good. Conductivity of the metal was too high, couldn't get fast pulses through it, and it wore away easily. It's too soft. So we chose cobalt zirconium tantalum alloy, a sputtered pole piece, and made a thin film head. It looks just like a disc head, only with cobalt zirconium tantalum material pole pieces. It's an amorphous material, harder, and it has high moment to write on metal particle tapes. So, because the coercivity of the media was considerably higher than chrome dioxide. You have a question?
No, I'm just following your numbers, though. You started with an 18. The actual module was an 18 head.
Yeah, each
18
module is 18 channels. One of them had
so
readers.
as you double
readers.
the capacity, or you go from 18 to, or you go from 144 to 288, your module width shrinks.
No, it's the same.
Same.
The only difference is you have more servo channels. So you can halve the pitch as the head moves across.
Half the pitch. So you double the elements in the module.
Double the number of servo reading elements. There's still 18 channels.
Yeah.
They're narrower now, and they move across twice as many times. to double the number of tracks. And you keep doing that again.
No, but you have a limited 1.5 inch width
Right.
for all of the tracks.
Yes.
So
The pitch
presumably,
changes. Yeah, the pitch is halved.
so if the module remains the same size, since the tracks are now half the width, you've got twice as many elements in that module, and aligning the modules, three modules, becomes a challenge.
Yes. The alignment of the three modules was a challenge because you go in both directions.
Right.
Now you can't use azimuth angle to align them because when you put one on track, the other one comes
It's off track, right?
Right, yeah. So it's a compromise there.
So is it still separately modules and you solve the alignment problem? I mean,
Yes.
you're still not at that.
No, we're still not. I mean, it's still fairly wide tracks, even at 500 on the tape.
Yeah, I mean, it's you're talking about a mil approximate.
Yes.
And you can,
That's
but
right.
then if you want, alignment to within 1/20th of the pitch,
Yeah,
I mean,
you can do that.
you're talking a 20th of a mil. That's getting
Yes,
pretty.
the alignment.
small,
Yeah, the
50.
alignment gadgetry got sophisticated. The mechanical guys who worked that out did obviously.
But you did in
We're
fact
given
solve that problem.
Yes. Right.
And again, keeping them aligned over temperature and humidity
Yep.
is another potential challenge.
You glue them together good.
I beg your pardon?
You glue them together really well. Okay.
At that distance, everything's made of rubber. There's no,
No, well, we used to use some sort of concrete. I can't remember what it was, but it seemed to do the job. Anyway.
really? Okay, I mean,
Yeah, it worked. But the other thing about that head was, I know we switched from ferrites to cobalt zirconium tantalum on the right head. The reed head was very different. And this is where the read-write group really got me in. Well, didn't get me annoyed, but we couldn't have the center-tapped device anymore because the reader was too narrow. In fact, the width of the reader was now the width of the center tap almost. Okay, so you had to go to a single-ended, what we called single-ended device, which was basically a stripe with two wires hanging off and two leads. And unfortunately, the feed-through was terrible because you did read while write. When you got 18 write heads turned on, every read head sees those write currents and fields from that head, even though you have a shield in there. We put a shield in between, which had to be mechanically stable. Couldn't be copper or anything, it's too soft. We used just regular brass, I think was sufficient. But still, there was enough leakage across the head surface that the signal-noise ratio was terrible when you're writing. So the question was how to solve that, and that was a head problem. Although I'd never admit anything would be a head problem, but anyway, so one design that had been proposed in the literature and various things was a dual stripe MR reader. I don't know whether you've heard of that. It's where you have, instead of having one stripe, you have two on top of each other, okay, with them joined at one side for the center lead, and the other two ends you sense differentially, which means now the feed-through signal went through the loop that was made by the read head circuit. One was in one direction and one was in the other. It was non-inductive, winding essentially. So the feeder was eliminated with this design. However, making 18 or 36 of these in a row with 100% yield, with films on top of each other, only 500 angstroms apart, proved to be difficult. In fact, and we're pretty much sure that's why nobody ever used this design. Okay, was because getting it to work. In fact, the gentleman in the corner office, the director, worked for IBM, and he liked the dual stripe design, but he said it could never be made, never be manufactured. They tried and failed and said no, it never could be done. And so we had to push back hard on that opinion, saying, well, that was 10, 15 years ago. The equipment's better now. The photolithography is better now. We need to give it a go, all right? So we did. And so we prototyped dual stripe readers with 18 or 20 of them in a row, because there were servo readers too. Outside the 18 there was pairs of servo readers to read that amplitude-based servo system. And of course the first prototypes we made all shorted out, just as predicted by the guy in the corner office. Okay. But then, as you know, like a lot of things, a miracle happens, right? There was one guy in the manufacturing line, the clean room. I'll have to remember his name because he deserves all the credit. He had a PhD. I tried to recruit him into the R&D group because he was really good. But taking him off the manufacturing line was probably a bad idea. He came up with a process to clean the first layer, because the problem was we did this lift-off process and you get these whiskers around the periphery of the photoresist. So when you put the second layer on top, they used to short circuit. He came up with a process to eliminate all those whiskers. It was a process called snow clean. You know how you bead blast things in a machine shop to clean them up with glass or sand to clean all the stuff off when you've welded it or soldered it or something? Well, he used a similar idea at a thin film level, and he used snow or small water crystals to blast the whole substrate, and it would knock all these whiskers off but not affect the base films. Put the next layer on top, work like a champ. 100% yield. In fact, we had better yield on readers than write heads. That thin film cobalt zirconium tantalum process was more difficult than the dual stripe read process in the end. It was because of that one process change that guy made. I really wish I knew his name, because he left the company in the end.
Keep thinking about it and we'll add it in.
Yeah, right. Because without that, life would have been a lot different. Okay, but because the dual stripe worked, we sent that head to the read-write group for evaluation, and they fell in love with the damn thing, right? Because the signal-noise ratio was fantastic now, because it eliminated all external noise input into the read channel. So, and it was a dual stripe reader, which means it could differentially detect and sense and eliminate second harmonic distortion and all the other good things that you like about differential bias and sense. And the other thing that I liked about it, all the thermal asperities went away. Because the thermal asperity on a tape comes across, as you know, it's like a hot match striking over the head, and it raised the temperature of the MR element, and you get a pulse on the MR signal, which typically unlocked the phase lock loops in the read channel. However, it hit these two. They were so close together, hit them simultaneously, and they were subtracted. I mean, it was like, they fell in love with their heads in the end, okay? The head group could do no wrong after that. So that was pretty good. Yeah.
I think at least one disk drive company did dual stripe.
It was on a floppy disk drive, I think.
No, I think it may have been somebody other than IBM did it, but then they all went to GMR as opposed to the
they went to GMR very quickly.
Yeah, but I think there was at least one company did AMR, actually shipped a product with an AMR head, and I'll check, and if I'll put it in the record.
Right, but this tape drive had I think we even shifted to two readers and a writer because the yield was so good on the reads in the end, and each read had 18 data channels and 4 servo channels, so that's 22, so that's 44 readers in one head. So to get yield on 44 tracks, 44 processed pieces, and we could use, and on that case, I think that's right. We still used ferrite shields for that device, for the reader, because it was separate from the writer. In other words, the write process was independent of the read process. You know, like disk heads, and you put a reader on a writer, one process mustn't kill the other one. And in this case, keeping them separate made it easier to perfect the read design or the write design independently. So that head was a real challenge, and it was interesting. It came out in the end, and the 3480 product was fairly successful, I believe. And because of its center load tape drive, fast access, and it was used pervasively in the banking industry for check imaging, I think, was the main use for it. So when you clicked on your bank statement, it would go and find the tape and load it in the tape library, and you didn't have to wait very long. Not the case now. Everything's on probably disk or solid state disk now. So.
I think today you are correct. But everything's backed up still to tape.
Probably.
No, it's just when you start talking petabytes.
Oh yeah.
There's simply nothing that compares in cost in some sort of mechanism to load. But you just can't. You can't store it. There's some smaller amounts are stored on nearline storage. Tape still dominates as I understand it, dominates the archival.
Yeah, the ultimate backup.
The ultimate backup. I mean, the near backup may in fact be on a disk array, but when you want to put something in Iron Mountain so it'll be there forever, you put it on tape and put it away.
Yeah. Anyway, so the 9840 series of tape drives went from double capacity and so forth, 2 or 3 iterations. I think it stopped at 576 tracks.
Okay, so it's through at least 2 iterations.
I think 2 or 3 iterations it had.
Now, tape is always, or for many, many years, featured down-level compatibility. Right. That's sort of the mantra in the tape, that the new drive should read at least 1, and I guess today 2 at most.
Right. Read down, yeah.
You can read the previous generation and maybe 1 more, but beyond that, you need a special system or some intermediate. Is that the case here?
Well, yeah, the latest one could read the first.
Read the first one.
Yeah. So
that's, of course, that as you pointed out, made it somewhat easier to predict what the next generation product would be. Just multiply it.
Well, see, this product was not IBM compatible.
No, but your next generation of 144 would be a 288.
Yeah.
Chances are. And then the next one beyond that would be a 576 if I could multiply by.
Yeah, and then I think I'm not quite sure what the last product of the sequence was. But because the media changed to get the higher areal density, they had to put a set of redundant readers in to read back to the first generation, because the new readers just
actually, you see that every once in a while where there's a hybrid which has 2 sets of heads, one for the latest generation and one for
to read the old stuff.
Read the old stuff.
Yeah, right.
So we're now through the mid-90s. You're still at StorageTek. You're still
StorageTek,
working on heads. At some point, you became a Storage Technology Fellow.
Yes, actually, that was I have it in the newspaper there. About 1994. I was recognized primarily for the fact that the tape head technology ended up being the key technology to enable StorageTek to...
The key messenger, to use your term.
Yes. Well, and in this case, the technology to... Because the media, we bought the media, we didn't make media, right? And tape drives, we had lots of mechanical engineers, did great tape drives, But that little piece in the middle, that magnetism and thin film design, was a key enabler for the company, I think.
But as a general rule, the media you bought came from an IBM standard or digital standard for DLT or Quick. I mean, those were. But when you went out to do this metal particle tape, the 9840, and in a cartridge, which I presume was your design, how'd you work that media out?
Well, we went to 3M, or no, Imation. now.
Same
Imation.
thing by then.
Yeah, Imation, and said, we want you to make this cartridge, and they produced a metal particle tape already for LTO 1, I think, the original LTOs. We said, okay, we want the metal particle media in this cartridge.
So it was the same.
So they got sole rights to manufacture the cartridge for us with StorageTek logos on.
So it was a standard tape that they were making for some other application.
I think so, yeah.
And the mechanics of the cartridge was your design, but you gave it to them with an exclusive license.
I think the mechanical people at StorageTek designed the cartridge. But I think the two groups the Imation group and that group worked together pretty well to come up with whatever manufacturable one there was. But and it was this dual reel with a window and door on it, you know, a little mechanism when you plugged it in, it opened the door and so forth.
Any idea why dual reel instead of...
Fast access, that was all.
So just to get in the middle?
Yep. Lower capacity because you get less tape in it.
Yeah. Interesting.
Okay, and it was the same. It was the same shape and size as the original 3480 cartridge, the square.
Square.
Yeah, but it had two reels in it.
Interesting.
Okay, and that was so it would be it would fit in all the tape libraries that were already out there. Okay, rather than having to have a different tape library.
Sure.
Or different racks or different something. So it was inside the same cartridge, and but it was two reels in it just to get fast access. Lower capacity because you get less tape in it, which also sped it up, by the way. So you had less tape, and then you put it in the middle of the tape. So you got about a factor of 4 in access time improvement, and that was attractive to people that were more interested in access time and
didn't want a disk drive.
Right. Yeah. Or disk drives at the time still weren't as dominant force as they are now.
And they were like maybe 1 or 2 gigabytes at that point in time.
Right.
Early 80s.
And this was a 20 gig.
Early 90s.
Yeah. Right. So it was a competitor then in that sense.
And reasonably successful.
Yeah, I think so.
So as a fellow, did your job change or?
A little bit. The notoriety, I don't know whether it sat with me very well, but I tend to hide away in this little lab, you see, for years and years and years, right? And now suddenly I'm put on stage sometimes, which is kind of interesting. But no, yes, the one thing that StorageTek wanted, there was another fellow also. The one fellow was Art Ruderseal, and then I was the second one in the company, and I think there was some others followed. But one thing that StorageTek encouraged, or the middle management did anyway, was for the fellow to do something new. You know, let out a bit of rope. You know, a bit of cash, a bit of money. Go and do something innovative that's not necessarily on mainstream. So I said, okay, I can anticipate that tape heads are going to have GMR in them someday. So why don't you go and buy me a sputtering system that can do GMR heads?
$250,000?
At least. So I said, okay. So I went and bought one. We bought it from Nordico, who was making them at the time. I hired another engineer who wasn't frightened of really thin films. I was kind of scared of 5nm films, or less. In fact, they were fractions of a nanometer. Okay? So I was a little bit scared of that in the sense that unfamiliar territory in terms of scale. So I hired a guy named Brad Engel out of, he was at University of Arizona and worked in the optical. And funny thing was with him was he was also started out being a low temperature physicist and ended up in a completely different discipline. But he was very good at these ultra thin films. And so we bought this buttering system and sent him off, said go make GMR films. And so we made the first spin valves at StorageTek with a tape head in mind. So that went on for long, because it turns out tape really didn't need spin valves for some time. You remember axiom number 1 is that the media is the problem. There wasn't the media to support the areal density where you needed a spin valve. But I thought that it would take a long time for the group and StorageTek to get a spin valve functioning with a fledgling 1 or 2 people on the side. But we did, and of course eventually they use them, and they're using them now. So, but it took a few years to get there. So that's one thing that happened, is I was allowed to explore a bit more, rather than a product in mind.
So you were still involved on the product side, but you had this separate budget and separate group that you could experiment with.
Yes, a little bit, yes. Wasn't very big, but it was enough to get it going.
And you picked GMR, spin valve, readers,
yes,
as
the thing that we would need one day. And eventually it came about. And all tape heads now have spin valve readers in them. They're not TMR or anything, they're straight spin valves. So still. So that was one change.
Has tape encountered the writing problem yet?
What do you mean the writing problem?
Well, the disk folks are pushing the point where they can't get enough flux density at the business end of the head to magnetize the particles with a strong enough coercivity that they'd like to have to keep the bits from reversing. It's the disk drive guys are fighting the so-called trilemma every day now.
Right. Well, they have been for some time.
For about 10 years.
Right, yes. That's what I said, sometime.
Yeah.
Right.
Yeah.
Yes. Well, no, the particles in a tape, the tape still uses particles, not thin films with grains.
Not domains of the film.
Right. And yes, the particles are small enough to have the same problem, the super paramagnetic problem.
They are.
Yes, they push that. They've been pushing that for about 5 years. But not in the sense of it's a problem. They just make sure they don't have any of those small particles that small.
But you can still generate enough field in the heads to, if you can get a particle, that'll work. Writing it is not the problem.
Right.
The physical chemistry of creating that particle is the problem.
Yes, that's where they're at.
It's a nice place to be.
Yes, right. That's true. Yeah, but by the same token. The moment thickness product of the magnetic layer on the tapes is such that you need spin valves, and have needed them for the last couple of generations to get, and that's why they have the higher areal density, lots more tracks. There's thousands of tracks, 2, 3, 4, 5,000 tracks on a tape, on a half-inch tape, and hundreds of thousands of bits per inch linear. Otherwise, you can't get 5 terabytes on a cartridge. Sure. But yes, so that's all true. That's the transition they made, and to get the signal-to-noise ratio with particles in a binder technology, the particles have to be small, and so they clearly have experimented with tapes where the particles have had thermal problems in R&D anyway. But so you don't use those tapes, you use the ones that are stable. So, end of story. But what happens next is, if there is another next in tape, is a more interesting issue. Again, in the media is the problem here, is what's the media going to look like if you want to up the areal density some more from where they are today.
But it sounds like that the messenger technology, to use your term, the head technology, and even the channel technology are more readily available than the media. The problem is the media today.
Yes, and that's because of the disk drive industry in terms of areal density, and that is ahead of tape, and always has been. Well, for a long time anyway, it's been ahead of tape. Maybe it wasn't originally in the beginning, but it is now, and has been for some time. So yes, the spin valves Well, they don't use spin valves anymore in disks, right?
I'm sorry?
They don't use spin valves anymore in disk drives.
Well, I think
They use...
the industry is adopting the term spin valve to talk about all of the technology. So a TMR, tunneling magnetoresistive head, is a spin valve in today's terminology.
Okay, all right. Well, it's TMR, it's not GMR then.
As opposed to AMR.
Right.
Right. They're all...
Yes.
Sorry. So as I was saying before the microphone fell off, the disk drive folks today, I think, use the term spin valve to apply to all sorts of magnetoresistive.
All right.
Technically, you might say spin valve really only apply to either AMR or maybe GMR.
Well, they don't use a TMR in tape at the moment, although it was always considered it could be a good fit.
And I think actually tape channels today are very, very much like disk drive channels.
Oh, yes.
They're just state-of-the-art digital channels, just you've got 18 running in parallel instead of one.
Correct.
Which is a different set of problems.
Yeah, that always, when I first worked in tape drives, that always fascinated me that a tape drive, when it writes the data, it reads it back immediately and checks to see whether it's correct on the fly, right? So it's running down there at hundreds of megabytes a second, doing a readback check immediately before it gets spooled up on the takeout spool. So you know the data is correct before it even gets spooled up. And it does it all on the fly in the electronics. And does it really fast, clearly. Because when you've got 18 channels, each channel running at don't know how many megahertz, and it's cross-checking all the data and checking the error correction codes and all that stuff to make sure it's correct. And if
disk drives don't do that at all.
No, and if it isn't correct, it stops the tape, backs up, and writes it again. Or it just writes it again on the fly. Doesn't even bother with the backup. Backing the tape up. Just keeps on going. Just writes it again. Okay? A little bit of capacity overhead required for that, but that's budgeted in. So.
Okay. No, that's from the disk side. It's disk drives really have always gotten away without doing a
readback check.
A readback check of any form. But
tape drives always do it. Always do it. Yeah.
About this time you leave StorageTek?
Well, Sun Microsystems purchased StorageTek in about 2005. Was it 2005? Yeah, about that. 2005. And I became a Sun Fellow because actually I was promoted to Senior Fellow at StorageTek just a few years before that. So I became a Sun Fellow by grandfathering in as the companies merged. And I didn't work in the head group much anymore. I worked on basically storage systems. And yeah, this is another thing that changed when I became a StorageTek and Sun Fellow, is that I was giving a lot more presentations and things and doing a lot less actual work, in my opinion, in terms of the technical stuff. There was an expectation level that had changed, that this is what you did now. You didn't do this technical stuff anymore.
Did you have a lab and a budget and other people?
No, that went away.
You were just by yourself?
Yeah, essentially. And I kept proposing to the company certain various things that they could be working on or doing, different storage device designs or concepts, and none of which panned out or were taken up. And but I found myself at a certain level, an expectation level, where I really wasn't doing much. It was kind of disappointing, and that's when I ended up leaving. It's because turns out Sun Microsystems, when one company buys another, historically, the old company tends to disappear. The people, they eventually go. They're either laid off, leave, or whatever. And that's what happened over the next 2 or 3 years at Sun Microsystems. And I was one of the ones that left. And as soon as that happened, the phone rang. It was Quantum. I said, "I hear you're not there anymore. Come work here." And so I went to work at Quantum.
This would be 96?
No, 2008.
2008. So you were, the acquisition of Sun was 2005.
Right.
I was off by a decade. It happens to be these more lately that I get my decade.
Right, yeah, well, after 9840, there came the T10000 drive, which was terabyte.
Mm-hmm.
I did a lot of promotion of terabyte tape in the industry, talks at NSIC, Mass Storage System Conference. Did a lot more of this giving talk things, and gradually a lot less of actually doing the head work. I guess that happens, right, to a lot of people. It happened to me too. So, and in the end, well, T10000, I worked on that, which was the terabyte drive. But after that, it changed, and I did more and more of this.
So let's pause there for a second and talk about your head activity in the T1000.
T10000.
T10000.
Yes, I promoted the idea of terabyte tape because after the last iteration of 9840, which got up to 200 gigs, I think in the end, 200 gigabytes, I said, well, let's do a terabyte tape. And most people said, that's 5x, there's no way you can do that. You know, the tolerances were so tight, and servo was up to its stops and everything in that tape drive. And I said, well, no, you just got to get the right media, and the head technology's probably there. There's already GMR in the wings over there. Can't you see it over there? See, and then so they started working on doing a terabyte tape, and I think I need to be checked on this. But was StorageTek the first to come out with a terabyte tape, or was it?
I don't know.
It was close, I'm pretty sure. No, I think the LTO came out. I think it was 800 gigs, or something like that, and StorageTek was a terabyte, and that was a pretty good. And that was a different concept of tape drive also. I think it had two heads in it. Two heads. One wrote the top half of the tape. One wrote the bottom half. Like this. And all channels running at the same time. So the data wasn't actually all physically located like it always used to be straight across the tape. It was downstream a bit, but logically and timing-wise,
Didn't matter.
it was buffered and it was fine, yeah.
And it was servoed?
Yep, went timing-based server on that one. Went away from the amplitude-based server, run out of headroom there, and so I went to a timing-based server. So you get more, and it turns out you do get more resolution with the timing-based server, just as the IBM guy said. So that's true. And that's why T10000 went to that. And the media was originally metal particle, I think, and now the subsequent tape drives that have been done in the last 5 years or so. Of course, I haven't worked there, so I don't really know. Is barium ferrite media. So, but anyway, so I cut a long story short. I went to left Sun and was immediately hired by Quantum. Wasn't sure I wanted to work there because of the work they wanted me to do. They wanted me to be a tribologist. Can you imagine?
After all these years in magnetism, to now move to tribology. But I have to say, my experience is that a senior guy in an area like heads probably knows a fair bit about tribology, having experienced the
wear and all the problems that tape does to tape heads.
Right.
I always had this story. I always had this thing that I said, the tape heads are fine until you run tape over them. Okay?
Right. Then the message gets distorted.
Yes. Right. Because normally the tape does all sorts of things to the head. It deposits rubbish all over it. It wears it away. You can imagine when it's two rubbing surfaces. I mean, and
If they are in fact rubbing, sometimes they fly.
Oh, they've pretty much been pretty hard contact now for the last 20 years. There's no way you can get the spacing low enough without hard contact because of the surface roughnesses and so forth of a particulate-based media system.
Well, disk drives still don't touch the...
I understand. That's a little tiddly thing. This is a big...
Yeah.
Anyway,
Yeah.
so it's a
big issue.
It's different. It's different, yeah. So, no, so I became a tribologist.
Oh, that's...
Kicking and screaming. No, I don't want to do it. And and I worked on it for about a year or so, but then I got, because Quantum was doing R&D for the LTO, heads and media was the name of the game in terms of how the two talked to each other. So I got also involved in the recording physics as well as the tribology. Started tribology and still did tribology. But I had some great techs. There's one gal there who was really good, Hong Ya Chen, a Chinese lady, did all my testing for me.
Would you repeat that name, please?
Hong Ya Chen. I think it was Hong Ya Chen. Yeah.
Chen, C-H-E-N?
Yeah. She did all the testing. She had tape drives, tapes. I said, these heads, these tapes, this humidity, this speed, this whatever. She go off, run the tests in the chambers, collate the data, take the photographs, microscope, SEMs, you name it, AFM profiles, collate the data, and give it to me. It's fantastic. Really was. And I could make an evaluation of, and I did my data analysis on that. So the drudgery of tribology, Hong Ya Chen took the drudgery a bit, all the testing, because it was fairly laborious.
Now, Quantum, at that time, and to this day, doesn't make anything.
Correct, as far as I know.
So
someone else makes it, and they put their sticker, their label on the front.
they label, but somehow the research you were doing
Right.
had to relate back somehow to the people who then designed the drives that were
Yes.
being made.
Yeah, there was a joint development agreement between Quantum and Hewlett-Packard.
With Hewlett-Packard. So you were doing essentially the head research.
Yeah.
To support the designs that were then going to be implemented.
Yes, and so I did the tribology there, and also got involved in the recording physics and some of the head design issues. If things didn't work quite right, I was able to give my input, given my background.
Now this should be some LTO
6.
6.
Well, it started out 5.
5, transit to 6.
And LTO 6, and also 7.
Okay.
So three iterations were in the works. I was also on a media group committee thing for LTO.
For the LTO.
Yeah.
Yeah, we talked at length when I was in Tucson about the structure of the LTO Consortium,
Okay, good.
which Quantum, I guess, joined
Yes.
late, but was a full member by the time you joined it.
Yes. Right.
So
I was on the media committee. So there was someone from Hewlett-Packard, someone from IBM, and me. And we did the media decisions, I guess, about what the media was going to look like for LTO 7. Then we get samples from the media providers, which were by this time getting to be 100% from Japan. So it was Sony, Fuji, Maxell, TDK, and Imation initially, but they dropped out, I think. So
today there are only 2,
and that is
Sony and Fuji.
Sony and Fuji, and they're probably arguing about various things too. But anyway, as I say, Maxell and TDK went. That's
So you would do the evaluation research, and then you would comment on the specifications being produced by the LTO Consortium. But
yeah, we gave the feedback to the media vendors, the head supply, and also the development group at HP. So, and I was kind of, because of my experience in pretty much everything there, I have my finger in all those pies. The Tribology pie, the recording physics pie, and the head pie, and the media pie. So, did a lot more work there than I had envisaged I might, which was good.
Mm-hmm.
It was good for me because, like I said, the latter years in Sun, I got pushed into this role that was essentially giving presentations and things, and it wasn't a very interesting job in that sense. You know, the quantum job was better.
Mm-hmm.
I was back in the lab again.
How did that, as a person who had taken his theoretical concepts, proven them as technology, taken them into production, now you're sitting here sort of on the side, still doing the research, but you've got to convince the IBM guy and the other members of the consortium. You can't reveal your trade secrets, but you got to somehow cause them to evolve standards and specifications that would work. How did that work for you?
Well, actually, I was fairly comfortable, really, because you get to the point where you've been doing it long enough that it becomes second nature, a lot of it. Which is why I came up with the 3 axioms. I said, this industry is governed by this. And as soon as you realise that, you know what to do now. Because all the media vendors knew I'd said this, and they all said they understand the media is the problem, and so whenever we didn't like something, we said it was the media, and it was true. There was this trade-off going on between some of the media characteristics and how well the head could handle it. This was the tribology thing, and of course you have to figure out how to solve that head-tape interface, because now in like LTO 6 and 7, the spacing between the magnetic portion of the media and the magnetic portion of the head had to be 20 nanometers or less. Now, for a disk drive, that may sound pretty big still, but this is a piece of gooey media, flexible media, scraping over a head, and that 20 nanometers has to be there for the life of the head, which has to be many years, not 10 minutes. Okay? And quite often there were head media combinations that only lasted 10 minutes before that spacing went from 20 to 40, and then all bets are off. No, couldn't resolve the bits anymore because of that spacing loss. So, no, it's the tribology thing was a big deal, and still is, I think. Although, fortunately, I don't work on that anymore, because it's not an exact science. It's a combination. It's physics, chemistry, electrochemistry, and so forth. It's all of these things happening all the time. There's ions going everywhere, moving around, chemicals oozing out of the tapes. And there's all these materials in the head. There's a spin valve in there, right? Spin valves. You know what's in there. There's copper, there's cobalt, there's all, you think of an element, it's in there probably. And then you want it not to erode away by 10 nanometers over years in an environment like this, or on a ship trucking up and down the Japanese coast, right?
Or in Hong Kong.
Yeah.
Where the humidity is...
Yeah, these aren't necessarily in nice controlled data centers. A lot of them are, but not necessarily. So that the tribology issue, and it turns out that came up with a solution in the late LTO, and you can look at the patents on that. There's a solution to that we came up with. No, I haven't worked at Quantum enough. I left there.
Can you
in
summarize the patent?
Yes, because it ended up that we twigged, or at least I twigged, that there's so many materials involved, so many 5 different tapes, vendors, different compositions and proprietary goo. And a lot of times in history, people have tried to put coating on a head to hide all this, but it typically wears off. And typically the coating has always been some sort of ceramic or diamond-like carbon or something that isn't diamond, okay? That's more of a marketing thing, I think, more than a real thing. And because of the electrochemistry and because the AMR elements are biased and you've got these chemical cells functioning, we worked a lot with Fred Spader at CMRR, because he's an electrochemistry type dude. That was his main reason for the cause of the erosion in tape heads, is because you've got voltages everywhere and you've got all this chemistry that you get all these ions running around, and it's this electrolyte soup that's flowing over the head all the time. So the thing to do is to try and get rid of all that. So the concept was to put a metal over the head. So you made the potential uniform. So there were no potentials now to drive the electrochemistry. And the one material I researched that I thought would work great was titanium. Okay, and the thing that put me off and some people originally was that titanium is a very volatile metal. And we said we don't want volatile things at the head group, on the head surface, which is why people were using ceramics and oxides and zirconium oxides and so forth to cover it. But it turns out that titanium, as you know, is an exceedingly reactive metal. It oxidizes almost immediately once you've produced it. And that oxide, that native oxide, is absolutely bulletproof. It's a bit on the same lines as disk drive TMR heads. They use magnesium, which they oxidize. They put down a fraction of a nanometer of magnesium and then oxidize it to form the tunnel barrier. It's the same concept, only with titanium it's a thicker coating. And I noticed that we've used titanium in the past to clean up sputtering systems because it grabs all the oxygen out of the residual gas because it's that reactive. But that TiO2 layer is absolutely, I wouldn't say it's hard, it's tough. And toughness is what you want in a tribology situation. You want it to be hard, but it's Young's modulus not to be too bad. In other words, it has to be a little bit springy. So when an impact comes, it comes back. It doesn't break off. If it's hard and brittle, it breaks off. But if it just comes back a little bit, and that coating has that. And I also did some research on, excuse me, that's my phone dinging. I thought I had it turned off. Actually, I do have it turned off. I don't know why.
It's probably my phone.
Oh, no, really? Okay, sorry.
Sorry about that.
It's the same ding. I looked it up, and I also, another little anecdote is years ago I broke my leg, and they put titanium metal bars in it. And the reason they use titanium is because of this oxide layer that's on it, and it doesn't interact with the body chemistry. It's not the titanium metal is underneath, it's strong, but it's that oxide coating that protects it from the body chemistry. And the same with submarines. They've got titanium hulls because they don't rot in the ocean, as well as not being able to be detected by magnetometers. And I looked up how the oxide forms, looked up some papers on that, and it turns out it forms approximately a 3 to 4 nanometer oxide layer in approximately 30 minutes. If you do a thin film, take it out, the sputtering system, just leave it in the lab. 30 minutes later, it forms a 3 to 4 nanometer oxide layer. I said, 3 to 4 nanometers, that's about right. So, is what we did. I did an experiment where I deposited 10 nanometers of titanium on the head. And I just said, do that and send me the head. Don't do anything else. So I did the head. They left it in the lab, clearly, and it oxidized. They didn't know what was going on. I got the head, ran tape over this thing, And it ran for hours and hours and hours and didn't change. Weeks and weeks and weeks and didn't change. So I proposed to the gang, you know, Quantum and HP, that we put titanium on the heads. And they said, Richard, you can't do that. It'll short all the MR heads out. Okay? I said, I know that. That's part of the solution, to short everything out. But you won't have any read signal. Okay. What we do is we hide the MR elements before we put the titanium down. The heads I've made, I didn't bother. Shorted all the MR elements out. I already know that. Okay? And so to cut another long story short, in the end, we put down 4 nanometers of silicon nitride over the whole head, and then 5 or 6 nanometers of titanium, which then oxidizes down to 4 nanometers and leaves another nanometer or 2 of titanium under it, for a total of about 10, which is half the 20, but it never changes. So every LTO 6 head now has that on it.
So it sounds like, from a technology point of view, at least in terms of tribology, you're pretty well running up against some fundamental limits. I mean,
Yes.
how many you make a 4 nanometer, can you make a 2? Maybe, can you make a 1?
Well,
I mean,
the thing about the titanium was that it made this 4 nanometer layer automatically. You didn't have to do anything. Now, if you tried to sputter titanium dioxide, it didn't work. You had to grow it natively.
Right.
It was a much more, and we had it tested. We took it to Rocky Mountain Labs over here, and did XPS and low angle X-rays, you know, spectra and so forth, and it was 99% TiO2 on the surface. No TiO and no Ti. And the other thing that was, this was marketing me. Sometimes I do marketing. That I said it's self-healing. If one comes off, the titanium just reoxidizes, okay,
Right.
and fills itself in. I'm not quite sure whether that was true, but,
Sure, but
conceptually.
and it was your colleague's idea to short it all out, and you came up with the titanium as at least one material that does a very good job of that.
Well, no,
summarize.
the idea was, well, I don't know whether it was a colleague or anything. It just sort of happened. Okay, well, if we electrically short everything out, then the electrochemistry goes away.
Right.
I mean, that's almost obvious, right? But the reason nobody had ever come up with it before said, well, it will short everything out, including the read signals. Well, I said, okay, we'll solve that problem later.
Fix the first problem and go work the next one.
Yeah. And then we ran the heads for 6 months, almost a year. The same head that we first did it on, and it still ran with the same SNR. Okay? So it was like a miracle almost, you know? There's 4 or 5 patents
Sure.
been issued by Quantum on that.
So I guess since Quantum, this was at Quantum. Quantum's a member of the LTO Consortium. They then contributed the patents to the consortium.
No idea.
So that, because it's sort of, if you have a patent on it, as good an idea as it is, you can prevent other people from using it. So the Fujis, you just don't know how Fuji and Sony worked with Quantum and the LTO Corporation to allow those patents to be used by them in producing.
I don't know anything about that.
I mean, it's sort of
The consortium and how it really worked, I really didn't get into. You know, I was the tribologist in the back lab.
Yep. It's an interesting, it's an outside observer, where the LTO concept was to set standards and specifications, but not tell people how to do the job.
You just had to be compatible with it. And
Just be compatible. Well, so the spec is it's got to last 6 months with this abrasive material. If it doesn't, you don't work. But if the only solution known is this particular patented material, how does that...
Well, I don't know whether it's the only solution, but it's the solution
It's a solution.
we came up with, and it seemed to work great. And I think it's still working.
Yeah.
But,
Well, and conception, well, it sort of it depends upon how broadly you can write the claim. I hope assuming Quantum has good patent attorneys, they would claim any metal.
Well, yeah, I think the first
that
claim
self-oxidizes. If you consider the listening to you, and I don't.
Yeah,
you could say you could write a claim that says coating it with a conductor that self-oxidizes, having previously insulated the MR without specifying materials at all, where the dimensions are on the order of 4 nanometers.
Yeah, I'm pretty sure there's some claims like that,
which are pretty broad.
And then the subsequent claims start talking
about titanium versus. Yeah, I mean that's the way.
And they might claim everything else, most of the periodic table.
So if your invention gets broad claims, such that maybe it comes from other way, but absent that, they sort of have to use.
Well, the issue is that IBM makes tape heads, but I don't think they put titanium on theirs. So maybe they have a different.
Maybe, but
or maybe they replace heads more often. We don't know that either.
Back to the days when IBM had a service engineer at every large tape account, changing heads every day on the 9 tracks.
I don't know. Yeah, I remember that.
I mean, we've come a long way, haven't we?
Yes, we have.
You mentioned, I believe at STC, you did a design for Aspen.
Yes.
Have we talked about that? Is it?
No, don't think so. It was. I don't know. When StorageTek acquired Aspen Peripherals,
okay,
they were producing a 4480 compatible
class product
tape drive, and they had an AMC head in it. This is now 10 years on. An AMC had actually managed to make something, but it was a thin film right head with bulk permalloy poles. And as that was their design, and also the reed head, the MR reed head was the same as similar to StorageTek's, only it was biased on the other side of the gap. Okay.
Okay.
So the question was, okay, StorageTek buys Aspen Peripherals. Aspen Peripherals makes a tape drive. They're buying tape heads from this company. StorageTek makes tape heads, makes the same tape heads that are compatible with that same tape. So why don't we put StorageTek heads in this drive? Okay, and so the answer is, what's it cost? These people were charging X dollars, and we could manufacture it for half that. So we had to make a tape head that would plug into that drive. Now remember, our tape head was a nickel zinc ferrite 2-turn writer. This was a thin film permalloy head with about 5 or 6 turns in it, like a disc head, but very thick permalloy poles. Our head would transmit 45 nanosecond pulses with a 2 nanosecond rise time. This head would only transmit a pulse that was about 150 nanoseconds long, and the rise time was about 40 nanoseconds because of the metal pole pieces. You just couldn't get a fast pulse through it. So they had to adapt their channel in order to write the tape properly to accommodate the fact that the head didn't respond to fast pulses. So we had to come up with a head without changing the tape drive now, okay, that would run off the same current as them with the same pulse train. So we said, okay, we'll go and do that. And so in the end, we ended up with a nickel zinc ferrite based head with 5 turns in it to get the right current the same. Now the inductance was up, so it responded a little slower, nowhere near as slow as the permalloy head. And then we demonstrated it in the Aspen tape drive in a similar manner that we did the IBM one years ago. And we put it in the tape drive, and it functioned, had very similar error rates and everything. And we had to modify the reed head so that the element was on the other side of the gap, so the phase shifting was the other way around. Okay, so in our opinion, it was a poorer choice because you're biasing off the glued-on closure. There was more tolerance in that gap than there was using the thin films as your guiding one. But be that as it may, we made the head that way round, and so everything worked fine. And then went to management and said, what do you want to do? We can make this head for half the price that they're paying for the AMC head. And they said, okay, let's make it. So, and what that meant was more volume was going through the head shop, which helped, as you know. You've got to amortize all that infrastructure, all those sputtering systems,
clean rooms
and all that. The more heads you can put through it, the cheaper they get. And so that helped. So that's the decision they made. And in the end, so all the heads were made at StorageTek for the Aspen drive. After that.
And I presume we're talking hundreds of dollars to buy a head.
Do you know what? My memory recalls that they were paying $1,700 a head.
$1,700 a head
for AMC, and we could make it for $800, I think. I mean, yeah, they estimated it would be about $800. And the reason they're that expensive is because the volumes were still low compared to what you see with disk drives today, where there's millions a week.
Yeah.
Okay, these are we're talking pretty low volumes.
A single head, single element, right? It's
well, I'll tell you another anecdote. I was a StorageTek fellow. New CEO comes in, wants to talk to me, right? And one of the things he wanted from us was he wanted a tape drive with a lower unit manufacturing cost. Okay? Okay, Richard, can you come up with our tape drives cost way too much to build, right? I said, well, how much do you want it to cost? He said, $500 unit manufacturing cost for a 18-channel, whatever it is, tape drive. I said, you get the tape head for that. Okay? That's all you would get, is the head for $500. He said, why is that? I mean, it's, you know, one component. I said, volume. If you can sell 1 million tape drives, I said, then you can have the head for $50. Okay? 1 million a year. They're only selling 25,000 a year at the time, or something, or whatever. I can't remember what it was now. Yeah. And I thought it was really funny. I said, I said, well, you get the head for that. But nothing. You can sell the head then, but it won't be a storage device.
So that was Ryle Papa?
Yeah. No.
Even later, the next guy?
Yeah. Pat Martin.
Okay.
Yeah. Ryle Papa came in to
84?
Yeah. Chapter 11.
Yeah.
Yeah. So he that's when he came.
Okay.
Yeah.
And then since Quantum, you've been consulting?
A little bit. Not much.
Did you move to California? Or
Moved
did you,
to California?
for Quantum, or you stayed out here?
Oh, no. No, Quantum had an office in Boulder. So, in fact, I didn't have to move house or anything. It was even a bit closer than StorageTek.
Okay.
So, and then they closed the building down in Boulder because it was on CU campus, actually. They were leasing a building, and they'd leased it for many years. And then CU wanted it back. So it was turfing all the lessees out of this building. And so they opened up an office in Louisville, over there behind Home Depot, and which was even closer. So, so that was so that was where they went at that time.
All right, so it's been a very interesting afternoon.
Mm-hmm.
You've been in the tape technology business. Actually, I take it some subsystem work at Quantum.
A little bit, recording physics.
Okay.
In terms of how the gaps interact with the tapes in terms of resolutions and spacing loss and frequency diagrams and so forth that channel guys like.
So like any senior technologist, your purview is a lot wider.
Yes,
than the...
and I think that's part of the reason that I was successful in the earlier years, or in the mid years too, is because I had a good grasp on the mechanical side, the electrical side, the magnetic side, and the media side and the channel side a little bit. I knew what they wanted. Spent a lot of time talking to the channel guys. So I had a broad view to enable to be successful in the head areas.
So taking that broad view, looking back, what do you think were the biggest accomplishments of the tape industry in the 35 years you've been involved? If you could rank them 1, 2, 3. And then looking forward, what do you think are the biggest challenges that the tape industry has as it goes forward for the next 10 or 20 years?
Okay, well, I think some of the biggest advances there, I'm still going to harp on the fact that the media is the problem, okay? But the media changes were important. I know you mentioned that offline before, but I mean, they were.
So that's
big changes.
From iron oxide to barium ferrite?
All the way through.
To barium, to cobalt chrome,
to metal particle. They solved the metal particle problem. Remember, when it first came out, it used to oxidize and degrade. They fixed that by coating the particles with something, yttrium something or oxide or something. Can't remember what it is now. And the metal particle tape enabled a rapid move, a more rapid move up the areal density curve. So that was important. The MR heads were there, and you could scale those. We talked about that. You can do that, and that happened. So that was straightforward. Another transition was being able to follow. Once the coercivity started going up and the areal density started going up, the shift from the heads from ferrite-based to thin film, full thin film based, that had to happen. There are lots of people or companies wanted piggyback thin film read-write heads like disk heads in tape drives a lot earlier than they needed to be there. But eventually we got there out of necessity because of the areal density growth. And so that was a big transition. In that, remember that gap in between the chrome tape drives and the metal particle drives, we shifted from ferrite-based, because of the lower coercivity, to cobalt, zirconium, tantalum-based write heads. And then eventually to spin valves when you got the lower moment media like barium ferrite. And being able to scale that coating down on the media was really, I think, impressive. Have you ever been to Japan and seen the coaters at Sony or Fujifilm?
No, I haven't. You have. Tell us about it.
It's amazing. They have these jumbo rolls of the substrate material, which is polyethylene naphthalate or PET, polyethylene terephthalate.
They used to be 24 inches, now they're 48 inches or probably millimeters.
Yeah, they're 4 foot wide jumbos and they weigh about a ton. Okay? 4 feet wide. And they run it through the coating machine. And this is what's most impressive, is that it goes through the coating machine at 10 meters per second. Now remember, the latest tapes are only, the substrate is only 4 microns thick. So this film, 4 feet wide, 4 microns thick, running at 10 meters a second through a coating machine. And it puts down an underlayer, okay? And on top of that, it puts a less than 100 nanometer thick magnetic layer that contains particles, you know, and wear particles and everything else, to plus or minus a nanometer. Okay? And it goes through a dryer. If it gets oriented, it goes through a magnetic field, and it gets spooled up. And that's going at 10 meters a second. And it doesn't break. Can you imagine if something happened to that machine? And it unraveled itself. You've got a ton of material spinning at, I don't know what the RPM is, but watching it is like mind-boggling. You've got to get out of the way in case it breaks, you know. But to get that scale, you know, what is it? I think the coating thickness is down to about 60 nanometers, okay, over a 4 foot wide roll at 10 meters a second with thickness control is pretty amazing. And it's not that they invented that. I think they've been doing it for so long that it's an evolutionary process improvement thing. you know, because they were coating. Originally, it was 100 microns thick, and then it was 50 microns thick, and then it was so and so, and then it went to 2 layers and so forth, and they put 1 layer down. And then it has to be dried and calendared. Calendering is like putting it through a wringer to flatten it all out, get all the bumps off, and that's really impressive to see that running. And that is why tape is so economic. The scale, the sheer scale of it. They can make millions and millions of miles of tape in an afternoon or something, or a run, you know, which is why tape's cost effective in that sense, because even if the tape drives are expensive, you run a lot of tapes through them, so it amortizes itself. So I think the media progression has got to be it. I won't say that the tape head is also, because of the sheer yielding problem of the multiple channels. There were 64 devices in a 9842 head, 64 magnetic things to get a yield of 1. Okay? In a disk drive, you only have 1 or 2 things to get a yield of 1. Right?
And you can replace each one if it's bad. So, right. I mean, even
you have to get all 64 elements correct. So the yield on each element has to be, I don't know how many 9s you have to get to before you get that. But so that's pretty impressive to do that.
So what do you think of the challenges now looking forward?
I'm going to say it again, the media.
The media.
Because particles in a binder have been so successful, it's hard to think how you can make a disc thin film-like media stand up to the rigors of scraping it over a tape head. Because you have to scrape the air off to get it down, to get the spacing to... Right now, I don't know what the spacing is in LTO 7, I think, but I was working with 20 nanometers as a number. It might be 10 now, but the coating on the head is already 10. So there's no flying like there is in a disk drive. You are in hard contact. And as you know, pure metals, if they're oxides, it's different, like the titanium thing worked, but that's not magnetic, so that won't work. But I think it's going to be tough to come up with a media to keep the areal density progression moving rather than it just stagnating. Has the areal density curve in disk drives stopped, or is it still going? I know the capacity.
That's a subject of debate.
Because the capacity of disk drives is still going up, but I know how they do that. They put more disks in the package, and so forth. But
so I track disk drive areal density pretty closely.
Okay.
And right now, it's sort of a learning curve improvement, 15% a year at best. In other words, they have a distribution of particle size and making it narrower, so
right.
the mean particle
I was asking a guy years ago, I said, so how are you making the areal density gains? And he said particle size distribution in the media.
Right, so
that's all they can do.
That's all they can do because they can't push it much smaller.
Yeah.
So the density is increasing, but it's at such a low rate compared to doubling every 2 years or 18 months. So what we see is new drives are coming out so to double the areal density takes 1.15 raised to the 5th or 6th or 7th power. So the doubling you see a doubling of areal density every 5 to 7 years now. Right. It's still improving, but not as fast as it used to because you're up against some real hard physical barriers. And it sounds like tape is...
If they want to stay with the particle in a binder,
they want to stay with the particle in a binder
thing, then they're already at the particle size. They're getting to the point. Well, if we go any smaller, we're going to suffer the same problem.
The metal particles are that small?
No, the barium ferrite particles.
Barium ferrite, so they have to go to metal particle.
No. Well, they went to barium ferrite because the moment was a little lower. Because you remember, it's a demagnetizing effect. That's the problem. You can do one of two things. You can raise the coercivity with a high moment, or you can just lower the moment. So the reverse field is not as high. The demag field is not as high. And that's what barium ferrite essentially did. And the issue with barium ferrite, of course, was when you make particles, they're in little plates shape. They're not little ellipsoids or circles, or spheres, rather. They're little plates, and they tend to stack up like poker chips. And now they look like a bigger particle. So the solution to that was not to orient them. So they randomize them and they don't stack. And I think barium ferrite media they're using now is randomized. It's not oriented media. And all that gives you is a different pulse shape, which means the channel guys have to come up with something to figure that out, which they do. And I'd like to give the channel guys some credit. I know I've been bashing them, and I bashed them a lot in the last 30 years, but the channels have done a lot to contribute to the areal density gain. Whereas you can have the same density on the tape, and then depending on your channel and how you look at it, you can get 1 bit per transition, 2 bits per transition, or 3 bits per transition. So you get more bits, data bits, for a similar magnetic recording. I've always said that the ones and zeros that come off a tape or a disc are in the imagination of the channel engineer.
Right.
Okay? Because the head delivers is an analog signal. It's a wiggly line on a scope. Somehow you've got to interpret that in ones and zeros. And you can do it in many different ways. You know, there was peak detect, whatever, and then partial response, and goes on and on, right? Various different ways. So every aspect of the recording system has had to make gains. It's not just the media, although that's the key. And the heads, in tape heads especially, the devices, the disk drive, because of its aero density, has been leading, I think, like leading with spin valves and so forth, and the tape has followed a bit. But the multi-channel nature of tape heads is the real challenge. And the fact you went from 9-track heads to, there's a 9840 head there with 64 devices in it to put down 576 tracks. That was, again, another move. And track following servo. If you look at the charts on some of the papers that have been written of areal density growth in tape, if you look at the slope of the areal density growth from the 50s through to 1992, it's one slope. And then after 1992, it's this slope. And that transition is track following servo. I know I've been giving the heads and media and channels a lot of credit, but track following servo is what made the transition.
See, I would argue that then what that shows is there was a technology, the change in slope shows the key technology breakthrough is track following servo, right. And the heads and media could then scale with just engineering.
There you go.
Right.
So there was
until it will then bend over.
Right.
That's what happened to disk drives.
Yeah.
I mean, in my view, not necessarily agreed to by everybody, but the change to thin film metal, sputtered metal.
Yeah. Media.
Media occurred, but thereafter the line took off, right. And now it's folding back over.
Right.
So we need another breakthrough, or maybe none's coming.
Yeah, because it's interesting because although track following servo was not a new concept, it was implemented.
Right.
That was the key. That's what changed in early 1990s in tape. It was implemented, and that changed the. Because it's a flexible media, right? I mean, tape's like a wet noodle, right? I mean, essentially compared to disk drives. And so it flops around and moves around over the head. And if you can follow it, your track density suddenly takes a leap. Yep. And that actually coincided with the transition from chrome dioxide to metal particle as well.
So in your view, if I could summarize, tape is pretty much up against similar problem as disk or flash, except the tape has if it can figure out a way to abandon particle in binder and move to a smaller domain,
Right.
then it can start scaling again. But otherwise,
And because it's all to do with signal to noise ratio. How many particles can you get in a bit?
well,
Right.
again,
And,
disk drives are down to about 7. You can't go below 1. 7 domains in a bit,
right.
maybe 9. It's that sort of number.
Yeah. But
It's a
that's
bit-
what happens is when the signal to noise ratio decreases because of that. That's where the channel guys have to come in to handle the lower SNR.
Yeah, but true, but there's a limit. At some point, you don't need any. You just put a white noise generator and correct it, right?
Yes. Okay.
Not a practical product.
No, maybe not. Yeah.
And so maybe that's a good point to end
Yeah.
today's discussion.
Yeah. Okay.
Anything you'd like to say in conclusion?
No, not really. I think my move to Colorado to work in this industry clearly was a good one. In terms of a career move.
Okay.
So that was definitely true. We came here and we did well. We raised 3 children. We live okay. The industry worked for us. So that's good.